Hello students, welcome to the 13th session of nuclear physics class. Myself Latha N, Assistant Professor of Physics, Government First Grade College, Sullia. Learning objectives of this unit were already discussed in the previous session. Topics covered in this session are nuclear charge, nuclear mass, nuclear density, binding energy, and nuclear angular momentum. First, we'll study about the nuclear charge. We all know that the nucleus is having positively charged. So why the nucleus is having positively charged? That is because the charge of the nucleus is due to the protons present in it. We know that the nucleus contains the charged particles, that is protons. Protons are positively charged particles, and the nucleus contains positively charged protons and neutrally charged neutrons. Therefore, the total charge of the nucleus is only depending upon the charge of protons. Therefore, the nucleus is having positive charge. Each proton is having positive charge of 1.6 into 10 power minus 19 coulombs. That is charge of one electron, that too in positive way. The nuclear charge is Ze. So if each proton is having 1.6 into 10 power minus 19, that is E. So if it contains Z number of protons, atomic number is nothing but the number of protons present in it. Ze will be the charge of the nucleus. The value of Z obtained from the nuclear scattering of alpha particles. So how we can obtain Z value is from the scattering experiments like alpha scattering experiment, X-ray spectrum. We can obtain the value of atomic number. This is about the charge of the nucleus. Totally, charge of the nucleus is Ze. It depends on the total number of protons present. And next we'll move on to nuclear mass. Mass of the nucleus is the sum of masses of protons as well as neutrons present in the nucleus. So we know that the nucleus contains both protons and neutrons. So both protons and neutrons are having mass. Therefore, the nuclear mass is the sum of the number of protons and sum of number of neutrons present in it. For nucleus having atomic number Z and mass number A, nuclear mass is represented by Z into Mp, that is mass of protons, plus A minus Z into Mn. Here Mp is the mass of the proton and Mn is the mass of the neutron. A minus Z gives the number of neutrons present. The mass spectrographs are used to determine the nuclear masses. So, experimentally, we can determine the mass of the nucleus using an instrument called as mass spectrograph. But as we measure the mass of the nucleus using mass spectrograph, the real nuclear mass, which is calculated using the formula Zmp plus A minus Z into Mn, is greater compared to the measured mass. Or the real nuclear mass measured using mass spectrograph is less than the calculated mass, that is Zmp plus A minus Z times the mass of neutron. So there is a difference. That difference is called as mass defect and it is denoted by delta M. Since there is a change in the mass between the measured value and the calculated value, the difference between the measured and calculated values are called as mass defect and it is represented by delta M. So delta M is equal to, so this is the calculated value ZMP plus A minus Z into Mn minus capital M will be the mass or real mass measured using the mass spectrograph. Nuclear masses are measured using a unit called as atomic mass unit. In simple, we can represent it as AMU. So AMU using carbon 12 as standard because the packing fraction of carbon is 0. So why we take carbon 12 is the packing fraction of carbon 12 is 0. That's why we represent the atomic mass in terms of atomic mass unit of carbon 12 isotope. Therefore, one atomic mass unit is equal to 1 by 12th of mass of one carbon 12 atom. That means 1 AMU is equal to 1.66 into 10 power minus 27 kg. That is the value of one atomic mass unit. Next, we'll move on to nuclear density. So, the nucleus occupies a very small space inside the atom. So, we know that the nucleus is 10,000 times smaller than the atom. That means it occupies a very small region inside the atom. And almost the entire mass of the atom is concentrated to the nucleus. Even though the nucleus is very small in size, but the whole mass of the atom is confined or concentrated at the nucleus. Hence, the nucleus is having very high density. Therefore, nucleus is having very high density. Nuclear density is calculated using formula nuclear mass divided by nuclear volume. Generally, density is calculated as mass by volume. Here we are calculating the nuclear density. Hence, we are using the formula nuclear mass divided by nuclear volume. We know that the nuclear mass is A into mp. A into mp is the mass of the nucleus. So it is the sum of mass of protons plus mass of neutrons. A is the atomic mass. Atomic mass contains number of protons as well as number of neutrons. Nearly mass of proton is nearly equal to mass of neutron. Therefore, nuclear mass can be expressed as A into mp divided by volume. So we assume that the nucleus shape of the nucleus is spherical. So volume of the sphere is given by 4 by 3 pi r cube, where r is the radius of the nucleus. We have a relation connecting the radius of the nucleus and atomic mass, that is r is equal to r naught a power 1 by 3. Substituting these two will get a mp divided by 3 by 4. R is equal to r naught a power 1 by 3. So if we substitute in place of r cube, then it becomes r naught cube into a. Then on simplifying this expression, a will get cancelled. The density of the nucleus will be equal to 3 mp divided by 4 pi r naught cube. So you can observe here the density will not depending upon any atomic number or atomic mass. Substituting the value of mp, that is 1.6 into 10 power minus 27, and r naught value is 1.3 into 10 power minus 15 whole cube. D becomes 1.8 into 10 power 17 kg per meter cube. So the nuclear density is of the order of 10 power 17 kg per meter square. Since the density of the nucleus is independent of atomic mass, its value is almost same for all nuclei. Since it is independent, it doesn't depend on the number of protons or number of neutrons. Therefore, it is independent of atomic mass. So, therefore, all nucleus is having the same density. The nuclear density is 1.8 into 10 power 17 kg per meter cube. It is equal to the density of neutron star. So therefore, we can compare the density of the nuclei with the density of neutron star. You are studied in the astrophysics how dense the neutron star will be. Therefore, a neutron star packs the mass of one or two suns into a sphere of about 10 kilometer in radius. ಎರಡು ಅಥವಾ ಮೂರು ಸಣ್ಣ ಮಾಸ್ನ ಒತ್ತಿ ಒತ್ತಿ 10 ಕಿಲೋಮೀಟರ್ ರೇಡಿಯಸ್ ಇಟ್ಟಾಗ ಎಷ್ಟು ಬರುತ್ತೆ ಅಷ್ಟು ಹೈಯರ್ ಡೆನ್ಸಿಟಿ ಇರುತ್ತೆ. ನ್ಯೂಟ್ರಾನ್ ಸ್ಟಾರ್ದು ಡೆನ್ಸಿಟಿ ಎಷ್ಟಿರುತ್ತೆ ಅಂದ್ರೆ ಒಂದು ಸ್ಪೂನು ಒಂದು ದೊಡ್ಡ ಆನೆಗೆ ಸಮನಾಗಿರ್ತದೆ, ಅಷ್ಟು ಡೆನ್ಸರ್ ಆಗಿರುತ್ತೆ ನ್ಯೂಟ್ರಾನ್ ಸ್ಟಾರ್. ಸೊ ನ್ಯೂಕ್ಲಿಯಸ್ ಕೂಡ ಡೆನ್ಸಿಟಿ ಅಷ್ಟೇ ಇರ್ತದೆ ಅಂತ. ನೆಕ್ಸ್ಟ್ ವಿಲ್ ಮೂವ್ ಆನ್ ಟು ಬೈಂಡಿಂಗ್ ಎನರ್ಜಿ. Mass of a stable nucleus is less than the sum of masses of neutrons and protons inside the nucleus. ಸೊ ನಾವು ಆಗ್ಲೇ ನ್ಯೂಕ್ಲಿಯರ್ ಮಾಸ್ ಸ್ಟಡಿ ಮಾಡಬೇಕಾದ್ರೆ ನಾವು ಮೆಷರ್ಡ್ ಮಾಸ್ ಏನಾಗಿರುತ್ತೆ, ಇಟ್ ಈಸ್ ಆಲ್ವೇಸ್ ಲೆಸ್ ದ್ಯಾನ್ ದ ಕ್ಯಾಲ್ಕುಲೇಟೆಡ್ ಮಾಸ್ ಆಫ್ ನ್ಯೂಟ್ರಾನ್ಸ್ ಅಂಡ್ ಪ್ರೋಟಾನ್ಸ್ ಸಮ್ಗಿಂತ. ಸೊ ಯಾಕೆ ಹಿಂಗಾಗುತ್ತೆ ಅಂದ್ರೆ ದಿಸ್ ಈಸ್ ಡ್ಯೂ ಟು ಕನ್ವರ್ಷನ್ ಆಫ್ part of mass energy of the particle into binding energy. ಇನ್ಸೈಡ್ ದ ನ್ಯೂಕ್ಲಿಯಸ್ ಅಲ್ಲಿ ಏನಾಗಿರುತ್ತೆ ಅಂದ್ರೆ ಅಷ್ಟು ಹೈ ಡೆನ್ಸಿಟಿಲಿ ಪ್ಯಾಕ್ ಆಗಬೇಕಾದ್ರೆ ಸರ್ಟನ್ ಅಮೌಂಟ್ ಆಫ್ ಮಾಸ್ is converted as energy. That type of energy is called as binding energy, ಅಂದ್ರೆ to hold the particles together. ಹಾಗಾಗಿ ಐನ್ಸ್ಟೀನ್ಸ್ ಮಾಸ್ ರಿಲೇಷನ್ ಪ್ರಕಾರ ಸರ್ಟನ್ ಮಾಸ್ is converted into ಎನರ್ಜಿಯಾಗಿ ಕನ್ವರ್ಟ್ ಆಗಿರುತ್ತೆ. ಹಾಗಾಗಿ ನಾವು ಎಕ್ಸ್ಪೆರಿಮೆಂಟಲಿ ಮೆಷರ್ ಮಾಡಿದಾಗ ಏನ್ ಬರ್ತದೆ ನಮಗೆ ಮಾಸು ಕಡಿಮೆ ಬರ್ತಾ ಇದೆ, ಯಾಕಂದ್ರೆ ದಟ್ ಎನರ್ಜಿ ಇಸ್ ಕನ್ವರ್ಟೆಡ್ ಇಂಟು ಬೈಂಡಿಂಗ್ ಎನರ್ಜಿ ಆಫ್ ದ ನ್ಯೂಕ್ಲಿಯನ್ಸ್. ರಿಲೇಷನ್ ಬಿಟ್ವೀನ್ change in mass and the binding energy which is given by Einstein's mass energy relation, that is binding energy EB will be equal to delta m c square, where delta m is the mass defect. The binding energy of the nucleus na ಹೇಗೆ ಡಿಫೈನ್ ಮಾಡ್ತೀವಿ ಅಂದ್ರೆ it is defined as the energy which must be supplied to the nucleus to break the nucleus into its constituent ions. ಅಂದ್ರೆ it is the energy supplied to the nucleus to break that nucleons. ನಮಗೆ ಗೊತ್ತಿದೆ ನ್ಯೂಕ್ಲಿಯಸ್ ಇಟ್ಸ್ ಕಂಟೈನ್ ನ್ಯೂಕ್ಲಿಯನ್ಸ್. ಆ ನ್ಯೂಕ್ಲಿಯನ್ಸ್ ನ ಸಪರೇಟ್ ಮಾಡ್ಲಿಕ್ಕೆ ಎಷ್ಟು ಎನರ್ಜಿ ನ್ಯೂಕ್ಲಿಯಸ್ ಮೇಲೆ ಹಾಕಬೇಕು, ದಟ್ ಈಸ್ ಕಾಲ್ಡ್ ಅಸ್ ಬೈಂಡಿಂಗ್ ಎನರ್ಜಿ ಅಂತ ಕರಿತೀವಿ. The binding energy of the nucleus with atomic number Z and mass number A is given by. ಸೊ ಅದಕ್ಕೆ ಈಕ್ವೇಶನ್ ತಗೊಳ್ಳೋದಾದ್ರೆ ನಮಗೇನ್ ಬೇಕು, ಮೊದಲು ನ್ಯೂಕ್ಲಿಯರ್ ಮಾಸ್ ಎಕ್ಸ್ಪ್ರೆಷನ್ ಬೇಕು. ವಿ ಹ್ಯಾವ್ ದ ಎಕ್ಸ್ಪ್ರೆಷನ್ ಫಾರ್ ನ್ಯೂಕ್ಲಿಯರ್ ಮಾಸ್, ದಟ್ ಈಸ್ Z ಇಂಟು ಮಾಸ್ ಆಫ್ ಪ್ರೋಟಾನ್ ಪ್ಲಸ್ N ಇಂಟು ಮಾಸ್ ಆಫ್ ನ್ಯೂಟ್ರಾನ್. Z is the number of protons, N is the number of neutrons. Where N is equal to number of neutrons, that is A minus Z. Here Np is the mass of proton, Mn is the mass of neutron. Let capital M be the observed mass. The difference in the assumed and observed mass is given by delta M, which is equal to Zmp plus N into Mn minus M. That is called as excess mass or mass defect. Therefore, the binding energy is equal to mass defect times c square. So mass defect is ZMP plus NMN minus M into c square, that is equal to the binding energy. Since ನಮಗೆ ಗೊತ್ತಿದೆ ನಾವು calculated value it is always greater than the measured value. That's why binding energy is always a positive quantity. So ದೊಡ್ಡದಿದ್ದು ಇದು ಚಿಕ್ಕ ಕ್ವಾಂಟಿಟಿ ಇರೋದ್ರಿಂದ so we'll get always a positive quantity multiplied by c square. Therefore always binding energy is a positive quantity. Value of binding energy varies from 2.23 mega electron volt to 1640 mega electron volt. ಈ ಕಡಿಮೆ ಬೈಂಡಿಂಗ್ ಎನರ್ಜಿ ಎಲ್ಲಿರುತ್ತೆ ಅಂದ್ರೆ ಫಾರ್ ಲೈಟರ್ ನ್ಯೂಕ್ಲಿಯಸ್ ಇರ್ತದೆ ಅಂಡ್ ಹೈಯೆಸ್ಟ್ ಬೈಂಡಿಂಗ್ ಎನರ್ಜಿ ಯಾವ್ದಕ್ಕೆ ಇರುತ್ತೆ ಅಂದ್ರೆ ಹೆವಿಯೆಸ್ಟ್ ನ್ಯೂಕ್ಲಿಯಸ್ಗೆ ಹೈಯೆಸ್ಟ್ ಬೈಂಡಿಂಗ್ ಎನರ್ಜಿ ಇರುತ್ತೆ. ಯಾಕಂದ್ರೆ ನಂಬರ್ ಆಫ್ ನ್ಯೂಕ್ಲಿಯನ್ಸ್ ವಿಲ್ ಬಿ ಮೋರ್, ಹಾಗಾಗಿ ಅವನ್ನ ಬೈಂಡ್ ಮಾಡ್ಕೊಳ್ಳೋಕೆ ಬೇಕಾದಂತ ಎನರ್ಜಿ ಕೂಡ ಜಾಸ್ತಿ ಇರ್ತದೆ. ಹಾಗಾಗಿ ಬೈಂಡಿಂಗ್ ಎನರ್ಜಿ ವಿಲ್ ಬಿ ಇನ್ಕ್ರೀಸಿಂಗ್ ಆಸ್ ದ atomic number or atomic mass increases. So the binding energy curve is represented like this. Along y-axis we are represented the binding energy per nucleon in mega electron volt and mass number along x-axis. You can observe here for lighter nuclei binding energy per nucleon is highest and it will be increasing and decreasing, and finally as the mass number increases the binding energy curve per nucleon will be gradually slightly decreasing and becomes constant. This is about the binding energy. Next we'll move on to nuclear angular momentum. Like electrons, protons and neutrons will also have spin angular momentum and orbital angular momentum. ಎಲೆಕ್ಟ್ರಾನ್ಸ್ಗೆ ಹೇಗೆ ಸ್ಪಿನ್ ಇರುತ್ತೋ ನ್ಯೂಟ್ರಾನ್ಸ್ಗೆ ಮತ್ತೆ ಪ್ರೋಟಾನ್ಸ್ಗೂ ಕೂಡ ಸ್ಪಿನ್ ಆಂಗ್ಯುಲರ್ ಮೊಮೆಂಟಮ್ ಕೂಡ ಇರುತ್ತೆ, ಆರ್ಬಿಟಲ್ ಆಂಗ್ಯುಲರ್ ಮೊಮೆಂಟಮ್ ಕೂಡ ಇರುತ್ತೆ. The magnitude of spin angular momentum vector S is given by modulus of vector S is equal to square root of S into S plus 1 into H cross, which is equal to square root of 3 by 4 H cross, because S is equal to half. Half plus 1 is 3 by 2. 3 by 2 into 1 by 2 is 3 by 4 to H cross. That is the magnitude of spin angular momentum. And in the same way, the magnitude of orbital angular momentum vector L is given by vector magnitude of vector L is equal to square root of L into L plus 1 into H cross, where L is the orbital quantum number. So if spin vector and orbital angular momentum vector is there, then we can observe the total angular momentum of a nucleus is given by J, which is equal to L plus S. J is the maximum possible component in a given direction, and the magnitude of total angular momentum of the nucleus is given by modulus of vector J is equal to square root of J into J plus 1 into H cross, where J is the total orbital angular momentum quantum number. For both protons and neutrons, the spin S will be equal to half, because both protons and neutrons are fermions and orbital quantum number L is an integer. Therefore, J can take values from half, 3 by 2, 5 by 2. That means it contains only half integral multiples of Total angular momentum is also called as nuclear spin. J is an integral multiple of h by 2 pi when A is even, and A is an odd half integral multiple when A is odd number. That means you can observe here the atomic mass A is even, here J is integral spin. J is having integral spin. This lithium 37. So here the atomic mass is odd number. Therefore J will take odd integral, odd half integral spin. Because J is L plus S, means odd half integral spin. Here for hydrogen 1H2, A is even, J can take integral spin. For hydrogen 1H1, A is odd and J can take odd half integral spin. So therefore J can be having integral multiple of H by when A is even, and J is having odd half integral multiple when A is odd. This is about nuclear angular momentum. The references for this session are listed. Thank you.